I've got this flask of water and it's open to the air. Now, if we set it down and let it sit for long enough, what would eventually happen? Well, it would take a long time, but eventually all the water would evaporate away. What about the second flask? It's got a stopper in it. We let it sit, will all the water go away? Well, no. But is that because there's no evaporation? Incorrect. Molecules are evaporating, but at the same time, water vapor molecules are condensing back into the liquid. The air inside here would be essentially 100% humidity. But that leads us to another topic. How much water vapor is actually in here and how do we quantify it? That's something called the vapor pressure. Imagine this. Got the flask. Imagine I have a tank of dry air, 0% humidity. And I've got the dry air, 1 atmosphere pressure, dry air, 0% humidity, slap on the stopper. Now evaporation takes place. Eventually we get up to 100% humidity. And in fact, not only do we have the air in here, but we have the additional pressure of the molecules that evaporate. And that's what we call the vapor pressure. Now, imagine this flask on this hot plate. It's not boiling, it's just warm. Okay? Same experiment. Now I got to take hot air, in this case, hot air, 0% humidity, flush, 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 slap on the stopper. Still get evaporation. More molecules evaporate? Yes, when it's warmer I get more evaporation, and in fact more vapor molecules up in the air, and therefore I would measure a greater vapor pressure at the higher temperature. If we think about what the molecules are doing in the evaporation process, we realize that evaporation is a surface phenomenon. Consider our flask of water, but let's zoom in on the surface. In the picture, the parallel lines represent all the molecules that are below the surface. Since all of the molecules are moving around, those at the surface are trading places with those coming up from below. For example, let's just highlight a molecule down under the surface in red. It can trade places with a surface molecule. So now the red molecule is at the surface. In order to evaporate into the gas phase, it needs to have enough kinetic energy to escape. But recall that intermolecular forces are attractive in nature. So there's an attractive force with a corresponding potential energy trying to pull the molecule back into the liquid. This idea of evaporation, that molecules need enough kinetic energy to overcome the potential energy of attraction, leads us in two directions. Remember that the vapor pressure is the additional pressure that builds up due to the molecules that evaporate. The air above the liquid already has a pressure to it, but that pressure can increase due to evaporation. So first, what happens to the amount of liquid that evaporates as the temperature changes? And second, how will two materials with different intermolecular forces compare in vapor pressure? Regarding temperature, an increase in the temperature results in an increase in the speed of the molecules. They would have a greater kinetic energy. That means that more of them would go into the gas phase. More molecules evaporating leads to a larger vapor pressure. In general, as the temperature increases, the vapor pressure increases. If you actually make a plot of vapor pressure in millimeters of mercury versus the temperature in degrees C, it looks something like this. You find that the plot is not linear, but rather it is curved. There are a couple of points of interest on the curve. This data is for water. First, at room temperature, 25 degrees C, the vapor pressure of water is only 24 millimeters of mercury. So pressure does not build up very much in a stoppered flask at room temperature. The other point of interest is at 100 degrees C, where the vapor pressure is 760 millimeters of mercury. The fact that this point represents the boiling point of water and 1 atmosphere of pressure is more than just coincidence. We'll come back to this. Also, the curve doesn't stop here. It actually keeps going, and we'll have to consider this as well. But first, let's go back and consider the effect of intermolecular forces on vapor pressure. We just had this situation that shows some of the molecules going into the gas phase. But what if the attractive intermolecular forces were stronger? In other words, what if the molecules had stuck together more tightly? If they're harder to pull apart, there should be fewer that escape, and more gas molecules should be pulled back down into the liquid. The net result should be fewer molecules in the gas phase. We would observe that as a lower vapor pressure. So our conclusion is that as intermolecular forces get stronger, the vapor pressure decreases.